Hello everyone, my name is Samuel Breslin again, the Solar Gators integration lead. And today I'm going to be showing a walkthrough of our schematic designs for the microcontroller unit on all of our PCBs. So before we get started with that, I want to finish up something from the last video about the power designs that I forgot to talk about. So on all of our boards, we like to add a power status LED, which is an LED that sits between power and ground on our board and illuminates whenever the board is being properly powered. So to do that, it's going to be pretty simple. I'm going to take one of our 3.3 volts labels and copy it, a ground label and copy it, Control C, Control V. And then I'm going to go to Panels, Components, find one of our LEDs, Manufacturer Part Search, or I'm sorry, I'm going to go to Components and see if I can find an LED in our Solar Gators component library. So we'll go with a green 0603 LED. This one. There we go. There's our LED. And I'm going to connect this side. This side with the little paddle, that is the cathode, I believe, and should go to ground. Okay. Now we need one last part in between here, and that's going to be a resistor. I'm going to name this LED 1. So most of these little LEDs need a certain amount of current running through them, and more than that can damage the LED. So I believe that is usually around, and we can refer to data sheet for that amount of current that we're looking for. It's always good to, and like I said, I could give you guys all these values, but I want to show you guys how to find these values by going to the data sheets and doing these calculations yourself. Okay, so we're looking for a forward current of a little bit under 20 milliamps. So that is our absolute maximum forward current. Okay, so let's go back to our schematic and let's see how we can find a resistor value to give us this forward current. Oh, we also need one more value, and that is going to be the forward voltage drop. Let's see. Okay, I'm just going to tell you guys that the forward voltage drop is usually around 1.7 volts, I believe. So we take I'm going to do this calculation in some text, just so you have it. So we take our voltage that we're putting across the LED, 3.3 volts, and we subtract the voltage drop of the LED from it. So 1.7 volts. It varies on the color of LEDs. And that is going to leave us with 1.6 volts left across the LED, across the 1.6 volts left of potential. Okay, so we have 1.6 volts, and we want to turn that into, we'll say 10, or we'll say 15 milliohms. Or sorry, 15 milliamps. Okay, so the equation for that is V equals IR, most important equation for electrical engineering, and we're going to reformat that as V over R is equal to, or sorry, we will reformat that as V over I is equal to R, right? So we take the voltage drop that we have divided by the current that we're looking for to find the resistance that we're looking for. So that calculation is going to be 1.6 volts divided by 0.1 0.01 amps, and that's going to give us, I believe, 160 ohms of resistance. Okay, so we'll find a resistor for that value. Resistor, a 200 ohm resistor should work. It's about the, anything higher than that, right? So we maintain below our maximum amperage will work. And we'll call that, I believe, R4, right? We have an R3 over here. Yep. Okay, so there you go. There is the power status LED. I'm going to go ahead and save that work. Okay, so that is it for our power schematic. Now I'm going to create a new schematic by right-clicking on Integration Video, Add New to Project, Schematic, and I'm going to save that so I can name it. I'm going to name it MCU for microcontroller unit, and I'm going to go ahead and add our microcontroller. To do that, I'm going to go to Manufacturer Part Search, and I'm going to get the exact part number from another document. So that is the STM32 L496RG T6TR. And I'm going to go ahead and right click, place, and it's going to give us two different parts of one schematic symbol. So it is one part, right? It's a slightly different schematic symbol. What's this one? Okay, that's fine. I don't know why the schematic symbol looks a little different. It's not a big deal. Okay, so here's our schematic symbol. It gives you two parts, part A, or part B, and part A of the same schematic. Now this is going to be all of our power stuff. This is going to be all the rest of the microcontroller. So we're going to start wiring it up. But first I'm going to give it the name 1A and 1B. Okay. So we're going to start with the power stuff. Now, the first thing, and one of the most important things when doing schematic symbols for microcontrollers is what's known as decoupling, or sometimes is known as bypass capacitors. And those serve two functions. One is to protect the microcontroller from any slight fluctuations in the input voltage. And the second is to provide the microcontroller with a very localized store of current. So, a microcontroller is really just, thousands, hundreds of thousands of transistors. And whenever a clock signal happens, right, and the microcontroller is going to be doing an operation, tons of those transistors are going to be switching, which is going to draw a tiny spike in current. So you want to have all these capacitors that are really close to the microcontroller to provide that current. So I'm going to go to Panels, Components, Caps, and I'm going to do a 100 nanofarad capacitor. Um, 100 nanofarads is equal to 100 microfarads here. So I'm going to right click, and I'm going to use this 0402 capacitor. And I'm going to place one for each of these VDD pins, right? So I think I'm going to do, except for this VDD A pin, I'm going to do 4 of them. 1, 2, 3, 4. Or that's 5. Let me check my reference. 1, 2. Oh, never mind. I'm going to do 6 of them. 1 for all of these, and then 1 for VBAT. So 1 of these. So these are going to go very close to the microcontroller close to each of these pins. Yep. Sorry, just want to make sure I'm giving you guys good information. And I'm going to place one of those 3.3 volts flags. Again, double clicking on it to edit these settings. And there we go, 3.3 volts flags, as well as a ground flag here, or power port. And I'm going to name these 3, or C3, yeah, C4, or wait, yeah, C3, C4, C5, C6, C7, C8. And there we go, there's 6. Okay, so there's my capacitors, and I'm going to add 2 more capacitors of a larger value. I believe I'm going to do 4.7 microfarads. Right, so that is 47 times larger. Now the reason we do these larger ones, right, is to provide even more current, right, maybe not as close to the microcontroller, but also having these two different, the different sizes of capacitors, they filter out different frequencies of electrical noise, you know, better or worse, right? Components 4.7 UF. I'm going to go ahead and place these. These are going to be pretty large 0805 capacitors. And I'll move that out a little bit. There we go. And this will be C10 and C9. Okay. So there's our bypass capacitors, right? They're providing power to our microcontroller. These guys, these are all ground pins, so that's the easiest part to route up. Oops, ground. Amazing. And yeah, so there's one last pin, that is the reset pin. And this little bar over the name indicates that it's a active low or inverted pin. So that means that whenever the pin is pulled high, right, then it's not going to be reset, right? So you might think, oh, this is the reset pin. Whenever we put 3.3 volts on it, you know, the board's going to reset. But that's the opposite of what's going to happen because this is an inverted pin, right? So when it's high, it's not going to reset. When it's pulled low, it will reset. So we're going to go ahead and I'm going to introduce something called a pull-up resistor. And so what we're going to do is I'm going to go to panels. I think I'll do a 2K resistor for this. Right, so sometimes it's not on some schematic symbols, right? I don't know why the schematic symbol is slightly separate, but just it's good to show you guys on some schematic symbols, it's not going to be represented by a bar, but it's going to be represented by an extra N in front of the symbol. And you can call it N reset. Ooh, I caught a mistake. Should be like that. That is my bad. Wow, I almost ordered this board. See, guys, it's always good to go over your designs a million times. Okay, so ooh, I'm gonna have to look at that again, but let's ignore that for now. Yeah, that is a bad reference. Okay, so I'm going to place components 4.7K resistor, place it here, and wire it to here, and wire it to 3.3 volts. Maybe 3. Okay, there's a 3.3 volts. I believe this is going to be resistor 3 or 4 or 5. Resistor 5. Okay, so this pin, right, is being pulled up to 3.3 volts through a resistor. Then we're going to route this out, and we're going to place a net label PN tab, reset it over there, go back to editing. Oh, PN. Shoot. Get rid of that. Okay. And I'm going to rename this to N reset. Reset. Okay. So this is our net label. Here's our resistor. And the way this works is this net label, right? That's going to be eventually connected to our programming header. So that's going to be able to control the state that this is in. Now, naturally, this pin is going to be pulled up to 3.3 volts unless the programmer connects the pin straight to ground. Now, the current is going to sort of, and this is a bad analogy, it's going to sort of follow the path of least resistance, right? So we're going to go to ground because it's not connected through a resistor. And instead, it's going to go to ground because it's not connected to a resistor. Unless, obviously, ground is not connected, it's going to go through the path of least resistance, which is the path with the resistor, and go to 3.3 volts. So that is a pull-up resistor. You can have the same thing, but opposite, with a pull-down resistor, where it's being naturally pulled down. But then you can, if you wire it straight to 3.3 volts, that's going to be pulled up. This resistor also helps to not cause a short when you're connecting 3.3 volts directly to ground. But yeah, so there's that bottom section. Let's move on to the clock. Now I am going to just mostly copy and paste this and just explain it as I go, just for the sake of time. The previous videos, I believe, were a little long for my taste and for many of your tastes, so I'm trying to go a little faster. Okay, so let's talk about the clock. So I'm going to name this Y1, and obviously I'm going to show you guys still where to get all these components. So again, I don't believe this is from the Solar Gators library. I believe this part is from Manufacturer Part Search. No, it's not. Components. Yeah, right here. Okay, so this is the clock or the crystal oscillator, and this is going to provide the clock pulses to the microcontroller. So pins 4 and 2 get connected to ground, and pins 1 and 3 get connected to the microcontroller. These capacitors are, I believe they're called load capacitors, although that might be wrong. There is a great ST application note about sizing these capacitors for use with ST microcontrollers, and I'm going to link that in the description if you want to look at the equations for sizing these microcontrollers, or these capacitors. And essentially what you're doing is you're looking at the data sheet for your crystal oscillator, as well as looking at the stray capacitance of these traces in your boards in order to calculate what extra capacitance you need to add in these lines. And in this case, we're using 10 picofarads. So I'll name this C6, or 7, or 8, C8, no. Oh, I forgot we had a lot of capacitors over here. C11. C11, and name this C12, and this will be R6. And also that application note will tell you what to do with this. In 90% of cases, right, you can make this just a 0 ohm resistor, and you might ask, oh, if that's just going to be a 0 ohm resistor, why, have a resistor in there for the first place? Why not just make it a wire? Well, having that footprint for a resistor, whether it's 0 ohms or 1,000 ohms, lets you desolder that resistor and replace it if you need to. And then we have our net labels, MCU high speed in and high speed out. So I'll go over that, and I'll just basically redo this. Okay, so we have our clock. Oops, right here. Right now, our 2 capacitors I'm going to place right beside it and below it, and I'm going to connect the capacitors up to terminals 1 and 3. And I'm going to move them up a little bit. Okay. And now I'm going to connect the other lead of the capacitor up to pins 2, 4 into the other capacitor, and that will go straight to ground. Awesome. Now, the pins 2 and 3 will also go to the MCU through these two net labels. We will bring this down. So we have these two net labels. Go ahead and place them. And there you go. There is your clock circuit. So I'll delete that now. We have our clock circuit right here. Okay. So we have power. We have our reset pin. We have our clock circuit. Let's go ahead and connect our clock net labels to the microcontroller. So we're going to be using the PH0 and PH1 oscillator pins. You also have the option for sort of a slower oscillator here with the oscillator 32 in and out. That's for a 32.768 kilohertz oscillator. And you might think that's a random value, but it is half of, around 64,000, which is, I believe, the maximum value of a 16-bit number. So it makes sense when you're looking at it in like binary. If you're looking at the binary value, as opposed to the decimal value. Okay, so we have our clock and our microcontroller set up. Now we have, let me just look at my notes. We have, okay, so we did MCU, power, status LEDs. We haven't done status LEDs. Okay, let's go ahead and do programming. Okay, so for that, you need a programming header, so you can, upload code onto the board. For that, we're going to look at, connectors. Here we go. Oops. And like I said, I'm starting to sort of take more stuff from other schematics in order to sort of move these tutorials along a little faster. Okay, so you have serial wire debug, which is the way we upload code onto our board, as well as how we debug the boards, right? So if you've ever programmed before in sort of an integrated development environment, you have the use of a debugger, which allows you to step through code, and you can do that on a microcontroller as well, using a serial wire debugger. So this is the header for the serial wire debugger. It's a 10-pin header. So VCC, it wants access to whatever your board is running on. Ground is self-explanatory, and you also have a ground detect pin. NC stands for no connect, so you place one of these no connect flags here so that when you go and validate your design, it doesn't give you an error for not connecting it. Then you have your serial wire debug input output. You have your serial wire debug clock, and you have your serial wire debug, I believe that stands for output. Again, no connect, and you have that same, bar reset or N reset pin. I'm going to change the name to N reset. Right, so that's what's going to connect and control this pin over here. So yeah, so that's great. Now we need to find where on the microcontroller to put these pins. And to do that, you can use a tool called Cube MX or STM Cube IDE. Either one works. I'm not going to show you how to set up a project in that because that just takes too long. But I am going to show you sort of where we get these pin assignments from. At launch. Okay, so we have, this is, like I said, this is an integrated development environment for programming these STM boards. And one of the features of that is this nice GUI for setting up the pins of your microcontroller. So you set up a project, you tell it what microcontroller you're using. You see here we have STM32, L496RG. takes a while to open. And one of the features of this integrated development environment is once you choose that board, you can configure the pins of the board and the peripherals of the board. And we're going to discuss more about what peripherals are when I get to my embedded lectures. Okay, so one of the systems or peripherals that we can configure here under system is serial wire. And I believe we have JTAG 5 pins set up, right? So we have our serial wire debug input output on PA13, serial wire clock on PA14, and we have did we set up? I don't believe I set up SWO on this particular project. It does not like that. Conflicted with PB4. We can reassign that later. There we go, SWO on PB3. Okay, so let's go ahead and do that. First, let's take down some notes. We have serial wire debug input output on 13, clock on 14, and SWO on PB3. Okay, so let's go back here. And before I forget, we have, oh, is this the wrong one? Yes. Before I forget, we have digital input output on PA13. We have serial wire clock on PA14. And we have SWO on PB3. Okay, so I'm going to wire them up as so. And I like to keep this sort of style of having the connector on the opposite side. I believe it makes it look a little neater, right, when you have different length, when you have a different length of sort of net labels. Okay, so there's programming. We have done power for our microcontroller. We have done the clock for our microcontroller. We've done the reset pin for the microcontroller, programming the microcontroller, and then all that's left is going to be the boot and the status LEDs. Okay, so for boot, we're looking here for our boot 0 pin. I don't think I like this schematic symbol for the microcontroller. I don't know where I found the other one, but I like that one much better. That's okay. We'll go with this one for now. So for this one, go ahead and copy over what I have. Like I said, I think I made some mistakes over here, so we're going to change some stuff. Okay. All right, so this is the opposite example of what we showed earlier, right? So earlier I showed a pull up resistor, where this is a pull down resistor, right? So when the switch is here in this state, this pin, the boot 0 pin, is going to be pulled down to ground, which puts the board in a certain boot setting. When the switch is flipped up here, right, it's no longer connected, or sorry, when the switch is flipped down here, it's now connected straight to 3.3 volts, which means the path of least resistance is 3.3 volts, as high as not ground. And so that's going to put the board in a different boot state. And we can discuss more about that in the embedded lectures. And like I said, we need to place a no connect flag. Directives, generic, no connect, and switch 1. Okay, so that is it for that. Let's go ahead and reorganize this a little bit. Clock. I might have to make this schematic slightly larger. Okay, now the last thing we're going to do is our status LEDs. So I'm going to go back to the power section and copy and paste what we had for this power status LED. LED 2 and our 8. And we're going to replace this 3.3 volts flag with a net label. We're going to name it STM OK. Or I'm going to do underscore OK. And I'll name this one LED 3. And I'm going to name this one error. So this is going to be a way of sort of allowing the microcontroller to talk to us easily, right? Instead of having to plug into it. This one is going to be the STM-OK LED, which we're just going to have blink on and off. And like I said, all this happens in the programming. Blink on and off whenever the board is functioning. This is going to be an error LED that's going to come on whenever the board is functioning, but it's running into some sort of problem. And then we're going to place those STM-OK and error LEDs somewhere on our board, and we'll just look for 2 random pin locations that we have available. I'm just going to use the ones that I used over here. It looks like I used error LED and OK LED as PA0 and PA1. So the first pins on the board. So I will just copy those and paste them. Oh, that didn't work. So we have error is going to go on PA0 and STM-OK. Let's move that over a little bit so that we can bring them out here. There we go. Now we have status LEDs for our microcontroller. We also have the boot settings. We have the reset control. We have power, and we have the MCU itself, as well as programming and clock for the STM. So that's going to be it for this video. I know this one was a little faster paced than the rest. Let me know how you like that, or if I should go a little bit slower. Thank you.